Alrighty, how's everybody doing this morning? Cool. Okay, fantastic. All right, so today we're going to start with a review of what we talked about last time. So we discussed what is electricity. So we'll just remember that briefly. We'll go over some definitions of some key terms: current, voltage, and resistance. Talk about what those are and what they mean for electricity. And then we'll remember a little bit about programming. We'll remember a little bit about for loops in particular, because those are really going to play a key part in today's lab. And then we'll go on to our main topic for today. So the main topic is motors, and really we're going to be investigating a mystery. We're going to try and figure out how we can design some windshield wipers for a car. Okay, so we're going to build a circuit and make a program to make our motors go back and forth like this, kind of like windshield wipers on a car. Okay, so you can see that this is going back and forth, but you can tell that there's some problems if we were going to use this as a windshield wiper. It's kind of going all the way around in a full circle, right? That wouldn't work so well on your windshield. So you'd be wiping your hood as well. So we're going to work on this and see if we can fix this and make it a little bit better so that it just goes back and forth like an actual windshield wiper. Okay, so we're going to be investigating the mystery of how that works, how we can write a program to do that, and how the motors actually work to make that movement happen. So we're going to be looking at electric motors, and to understand electric motors, we have to understand a little bit about magnets. So we're going to start by talking about magnets, and then we'll go on and see how they play a key part in electric motors. And then we'll talk about a special type of electric motor called a servo motor, which is really an electric motor with a little computer brain attached to it. Okay, so we'll talk about that. And then we'll go on and do a preview of today's lab, where we'll get to write a program to actually make the motor go back and forth like I showed you. Okay, so that's what we'll be working on today. Any questions before we get going? All right, cool. So then let's get started with a review from last time. So last time we talked about electricity and what is electricity. So anybody remember a simple definition for electricity? Yeah. Yeah, yep. Hi. Electrons in motion, exactly. So electricity is electrons in motion. And we call those electrons, when they're flowing, we call that current. So yeah. So we said to really understand what this means, we have to understand what an electron is. So we said that all of matter is made up of these atoms, which are these tiny bits of matter that have a nucleus with positively charged particles called protons, and then an outer shell with negatively charged particles called electrons. And we said that the positive and negative charges want to stay in balance. So you want to have the same number of electrons with their negative charges as we have protons with their positive charges. And these atoms are all packed closely together when you have matter. And each one has its own electrons. And when you have the same number of electrons and protons on each of the atoms, then everything's happy and balanced. But it doesn't always stay that way. It's possible to push some extra electrons into this system. So you could shove an extra electron on here, and then that kind of throws things out of balance. when you do that, you end up with an extra electron orbiting this nucleus, and now you have too many electric charges. And the negative charges in this outer shell, they're not stable, so they tend to push each other away. And so oftentimes when you have extra electrons close to each other, they push each other away, and the electron ends up jumping from one atom to the next door neighbor. So then the electron goes over there, and you end up with the same situation. And maybe you shove on another electron over here, so this one can't come back, so it ends up jumping further on. So these electrons keep jumping from atom to atom. And this movement of the electrons, these electrons moving from one atom to the next, that's what electricity is. We call that electricity. So electricity is these electrons in motion. Okay? So when we're talking about electricity, that's all we mean. We're talking about the flow of these electrons from one place to the next. So any questions about that? All right. So then we talked about a couple of key terms that describe electricity. So the first one was current. So current, anybody remember a definition for current? Yeah, yep. So it's the electrons flowing. Really, yeah, it's how much electricity is flowing at a particular moment. So if we were talking about water flowing through a pipe, this would be like how many gallons per minute are flowing past. So current is how much electricity is flowing, how many electrons are moving past a certain point. So the unit for current is amps. And we said that 1 amp equals 6.24 times 10 to the 18th power electrons per second. So 6.24 quintillion electrons per second. So if you were to measure at a particular point in your circuit and you started counting 1, 2, 3, 4, 5, 6.24 quintillion, you'd get up to 6.24 quintillion electrons went past that point every single second. Okay? So that's what 1 amp of current means. So current is how much electricity is flowing. So any questions about that? Yeah?
Do the electrons change on the different voltage? So let's say you had 248 voltage going through 1 amp. Is that still the same amount of electrons per second?
So yeah, as long as you have 1 amp of current, that's 6.24 times 10 to the 18th electrons per second.
Got it.
Yep. Yep. Other questions? Okay. So then, yeah, that brings us to our next key term, which you mentioned, which is voltage. So anybody remember a definition for voltage? Yeah.
The rate of flow of electricity?
No, that's current. Yeah, the pressure. It's the force that pushes electricity through a circuit. Which is like electrical pressure. It's sometimes referred to as electrical pressure. So, yeah, so the unit is volts. And yeah, we said that if we were talking about water flowing through a pipe, then the voltage would be a pressure. So pressure is always measured as a difference between 2 points. So for instance, if you had a pipe and one end was higher than the other, you could measure the difference in the pressure from one end of that pipe to the other. And then that difference would be what you care about, right? The reason that pressure is always measured as a difference is imagine you have a pipe and it's full of say it's full of little tiny marbles, okay? And you kind of squeeze lightly on both ends of the pipe, and you're squeezing with the same amount of force on both ends. Are the marbles going to move from one side to the other? No, as long as you're pushing with the same force on both ends, it doesn't matter. They're not going to move. Now, imagine you started pushing really, really hard on both ends. Are they going to start moving at that point? No, as long as you're pushing the same force on both ends, they're not going to move. But when you push hard on one side and gently on the other, the little marbles are going to start moving from where you're pushing hard to the other side. You're going to start pushing them out. So it's always that difference. It's the difference in how much you're pushing on one end compared to the other. That difference is what determines how fast or how many marbles start moving, okay? So the same thing goes for water. It's the difference in height between these two ends of the pipe that make the water flow. So you could have a pipe down at sea level, 0 feet. If both ends of the pipe are at 0 feet, the water's not going to flow, right? You could take the same pipe full of water up to the mountains, 7,000 feet. As long as both ends of that pipe are at 7,000 feet, the water's still not going to flow from one side to the other. But when you raise one side just 1 foot higher than the other, now the water's going to start to move. So it's always a difference in pressure that makes the water flow. In just the same way with voltage, it's always a difference in voltage between one place and another that makes the electricity move from one place to another, okay? So voltage is this force, and it's always a difference between 2 points, okay? And the unit is volts. So any questions about that? Okay. All right, and then the last force that we talked about, the last term was resistance. So resistance, anybody remember a definition for that? Yeah.
It's the force that opposes the flow of electricity.
Exactly, the force that opposes the flow of electricity. So, so this is what makes it hard for electricity to move through a circuit. Again, if we were talking about a water pipe, this would be like a narrow spot in the pipes where it's hard for the water to flow past. So resistance is the force that opposes the flow of electricity. The unit for resistance, anybody remember? Yeah, it's ohms, and yeah, there's an abbreviation, which is the Greek letter omega, which does kind of look like an upside down horseshoe there. So, so it's important to understand resistance because sometimes we need to design circuits that have resistors in them that slow down or reduce the flow of electricity so that we don't drain our batteries or blow up our components. Also, every component has some amount of resistance. So we need to understand how resistance works and how it affects circuits so that we know how electricity flows through our components. Okay? So those are the three main terms that we discussed last time, and they're the three most important terms that that relate to the flow of electricity. Okay? And do you think maybe there's some relationship between these things? Like, you know, do you think that how much force you put on your circuit might affect how much current is flowing through it? Yeah. And maybe the amount of resistance might also have an effect on how much current you're having? Yeah. Yeah, so turns out that there is a relationship between all of these, and that is called Ohm's law. And that's really the most important formula in electronics. And we'll be talking about that later on in a couple of classes, okay? But yeah, just that's something to think about. All right. So those are the three terms that we discussed. And then we also talked a little bit about programming. So any questions about these terms before we go on? Okay. So we also talked a little bit about programming, and we talked about for loops in particular. So remember, a loop is something that makes a program repeat a certain section of code. And there were a couple of different types of loops that we looked at. So a do loop, how many times would the code repeat inside of a do loop? Forever. Exactly. It just keeps going and going. But a for loop was a little bit different. A for loop allowed us to control how many times the program repeated. So the syntax was something like for, not like the number 4, but for counter equals 1 to 5. And then we would have the code in the middle that we want to repeat. And then at the end, we would say next. And remember, so this is saying that we're going to use a variable called counter. The first time the loop runs, that variable is going to start at 1. And then we're going to go through this code, and we're going to get to next, and we're going to come back up, and then we're going to increase the variable by 1. So the next time, this will be 2, and it runs, and when it gets to next, that tells the program to jump back up to the beginning. And this is going to keep going until this variable gets up to 5. And then when it gets to 5, it's going to be done. So this tells the program to repeat something 5 times. And remember, we're using a variable here, and before we can use this variable in our program, we actually have to tell the program that we want to create that variable. So the way we do that is we use this line counter var byte. So that says we're going to create a variable called counter, and it's going to be 1 byte of memory that can store numbers between 0 and 255. Okay, so that's what we're going to do here. So that's the way that a for loop works, and we can change the number of times that the for loop repeats by changing this number here at the end. So if we wanted to make so this loop will repeat 5 times, but we could make that 10 or 50 or 100 or whatever we want. Okay. Anything up to 255. So are there any questions about how for loops work? Yeah.
So, oh, never mind. I didn't see I thought you had to put variable before counter, but you were putting it on there. I didn't see it.
Yeah. Yeah.
Would you have to put
counter or byte before each port counter, or just once?
Just once. Yeah, you only have to do that once. And you don't have to use the name counter. That was just the name that we've been using. So you could call it, you know, my var or something like that. Or you could call it Sally or Jim or whatever you like, really. Yeah.
So in this particular coding language, do you have to allocate memory for each like segment of code?
No, no. So yeah, some programming languages you have to tell the computer how much of its memory you want to use for a particular part of your program. But with this one, you do not. You just, the only time you have to tell it to use memory is when you're telling it that you're going to use a variable like this. Yeah.
And so byte is just iterating from 0 to 255 as a prime?
No, so a byte tells the computer how much memory to set aside. So a byte is 8 bits. It's 8 little ones and zeros. And that can store any number between 0 and 255. So there are also, you could replace this byte with word, I think. And I think that's like 16 bits, and that's like up to 65,000 or something. So if you know you're only going to be storing a small number between 0 and 255, you can use a byte, so you're only using up a small amount of the computer's memory. If you want to store bigger numbers, then you can tell it to put aside a whole word, which is 2 bytes. So you're using up more memory, but that means you can store bigger numbers that way.
So we can use 0 to 4 instead of 1 to 5.
I believe so. Yeah. So right. So you could start from 0 to 4. So then the first time that your program runs, your variable would be 0, and it would keep going until it would go up to 4. So then that way it would still run 5 times. Yeah. Mm-hmm. Yep. Other questions about that? Okay. All right. So then let's go on to our main topic for today, which is motors. So, like I said, when we're doing our lab today, we're going to build a program that makes a motor go back and forth, okay? So we're going to have a little servo motor like this, and it's going to go back and forth, and we want that to, we want to understand how that works, both from the programming point of view and also from the motor point of view. We want to understand how motors actually work. So let's think about an example. Let's imagine we're, way back in history, back when cars were first being built, and we're trying to design the first windshield wiper. Okay, so we're trying to design a windshield wiper that goes back and forth on our windshield to get the water off, but we don't really have a lot of information to go on. We're kind of starting from scratch here. Okay, so maybe the first way that we might think about getting that windshield wiper to go from one side of our windshield to the other might be with a magnet. So that might be helpful because a magnet attracts things. So if our windshield wiper is on one side of the windshield, we might want to attract that windshield wiper to the other side of the windshield. So I brought along a magnet here. So these are a couple of pieces of magnet. And as you know, magnets attract certain types of metal that have steel or that have iron in them. metal like steel. So if I take these magnets and I put them close to these paper clips, they pick up those paper clips right away, okay? Now, these magnets are called permanent magnets because they are permanently on. They don't take any power, they're just always on all the time, okay? No matter what we do, they're always on, so they're permanent magnets, okay? So they always attract these paper clips, and also they attract each other. So, a magnet has two poles, a north pole and a south pole, and the opposites attract each other. So if I put the north pole of one magnet close to the south pole of another, they attract each other and they stick together. But if I flip these around, so now the two north poles are close to each other, and I try to push them together, they don't want to go. They're pushing hard so that they won't touch. Okay, so the opposite poles attract each other, but the same poles actually repel each other. Okay, and these permanent magnets, like I said, they're always on. The poles are always in the same place. So this is, say, the north pole of this magnet. It's the north pole now. It's going to be the north pole in 5 minutes. Tomorrow it'll still be the north pole. It's always the same. Okay. The south pole will always be the same. So they're permanently aligned. They're permanently on. Okay. So I'll pass those around so you can take a look. They're pretty strong, so try not to get your fingers pinched between them. Okay. So those are permanent magnets. So that might be a good place to start. You could attract your windshield wipers from one side of the windshield to the other, but then when you get to the other side, you'd be kind of stuck because those wipers would be attached to the magnet and they're stuck, and that magnet is permanently on, and so there's no way to get those wipers unstuck and move them back across. All right, so it's kind of a first step, but it's not really what we want. So it'd be nice if there was some way to turn a magnet on to make the wipers kind of flip over to one side of the car, but then maybe be able to turn that magnet off again, maybe turn on a magnet on the other side to make the wipers come back. Well, it turns out that there is a way to do that. It's possible to create something called an electromagnet. So let me show you how that works. Let me grab a cable here. All right. So I have here just a really, really big nail, okay? Nothing fancy about that. If I put the nail close to my paper clips, it maybe picks up one or two, but so it might have a little bit of magnetism to it, but really not very much at all, okay? So it's slightly magnetic, but I'd like to make that strongly magnetic. So the other thing I have here is I have a long piece of wire. Okay. Again, there's nothing fancy about this wire. It's just regular wire. If I touch it to the paper clips, it doesn't pick up any paper clips. Okay. It's just a long coiled up piece of wire here. And now it's a long straighter piece of wire. So it's just this long wire. But if I take this long wire and I wrap it around the nail, then I can turn this nail into an electromagnet if I put electricity through the nail. Okay, so I've got this wire wrapped around the nail now. So now what I'm going to do is I'm going to hook it up to my power supply here. So this thing on the bottom of my cart is power supply. So if we plug this into the wall, this is going to create some electricity, and I can attach that to my nail, my coil of wire that's wrapped around my nail, and that should create an electromagnet. Let's see if it works. So I'll put this on. All right. All right. So turn this off while I'm making the connections. All right. So I've got my wires connected to my magnet there. And now, if I put this in the paper clips, you can see it's still only picking up maybe one paper clip some of the time. So it's still not really magnetic because I haven't turned on the power yet. So when I turn on the power, and now I put this near the paper clips, now it's picking up a lot more, okay? So now, by putting electricity through this coil of wire, I have created an electromagnet. And if I turn this off, it still retains some of its magnetic properties. But if I let go of these, and I try to pick them up again, most of that magnetism is gone, okay? And if I switch these around, and I turn it on for just a second, I bet we'll get rid of that. Yeah, so now all of the magnetism is gone. It's not even picking up one little tiny paper clip anymore, okay? So the main takeaway here is that when we wrap a coil of wire around a metal form and we push electricity through it, that creates an electromagnet, okay? So it's a magnet that we can turn on and turn off. And if we switch the polarity of the polarity of the electricity, in other words, if we make the electricity flow through the opposite way, we switch the poles of the magnet. So what I'm saying is, if we got this coil of wire and we push the electricity through in this direction, we can create a magnet with a north pole up here and a south pole down there, say, okay? But now, if we flip this around so the electricity is going the opposite way, now the poles get flipped also. So we end up with a south pole up there and a north pole down there. So again, if we have electricity going this way, we get north up here and south down there. If we flip it around, the poles of the magnet flip, okay? So this is the opposite of permanent magnets. Permanent magnets are always on, they require no power, and the poles are always in the same direction. Electromagnets can be turned on and off, they require electricity, and you can flip the poles depending on which way the electricity is flowing through the coil, okay? So this is great for our windshield wiper design, because now we have a thing that we can turn on to make the windshield wipers flop from one side of the car to the other, and then we can turn it off, and maybe we can turn on an electromagnet on the first side to make those windshield wipers come back, okay? So we're making progress towards getting those windshield wipers to go back and forth. But there's still a problem, okay? And that problem is that the closer something gets to a magnet, the more strongly it's attracted. So that's a problem for these windshield wipers, because at first you'd have to have that magnet be really, really strong because the wipers are far away. So you'd have to put a lot of electricity through there to get those wipers to start going. And then when they started going, they'd get closer, and so then they'd be stronger attracted. So then they'd start speeding up, and they'd get even closer and be more strongly attracted. So they'd go wham and like smack the other side. Okay, so because they're getting closer and closer and stronger attraction. So this would be kind of damaging to your wipers. They'd probably fall apart after just a couple of trips back and forth. And so that's not ideal. So we'd like something to have where we could have a little bit more control over these wipers. Be able to make them move at a nice constant speed from one side to the other and not crash into the end, okay? So maybe there's a way that we can take these principles that we've learned about and use them to make some motion that's a little bit more controlled. And really, that's what an electric motor is, okay? So an electric motor uses these ideas that we've been talking about to move things around, but it does that in sort of a much more controlled manner than just on-off control with a electromagnet. So the way that a typical electric motor works is that you've got an axle that's sticking out of the motor, and the way I'm going to draw it would be like the axle is sticking straight out of the board here, okay? So it's pointing out of the motor towards you. So right in the middle here, we have this axle, and we want to make this axle turn. So this will be good for moving our wipers back and forth. It would be good for, making a car drive if that was attached to a tire. So we want to turn this axle, and we want it to keep turning in the same direction so that our car can keep driving forward, say. So the way that a motor does that is that there is a bar of metal attached to this axle. And say the bar of metal starts off kind of in this position here. And this bar of metal has a coil of wire wrapped around it. And this coil of wire goes all the way around and around this bar, there is a circular metal frame. And this frame has permanent magnets mounted to it. So these permanent magnets have poles. Say there's a north pole up there and a south pole down there. And then you have a permanent magnet at the bottom as well that also has a north pole and a south pole. And then you put electricity through this coil of wire so that you create a south pole up there and a north pole down there. Okay? So this bar of wire, or I'm sorry, this bar of metal is free to rotate around the axle, and it's trying to turn this axle around. And so what happens is that when you get a south pole close to a south pole, what do they do to each other? Yeah, they push each other apart. So this south pole is pushing this south pole away, so it's trying to turn the bar that way. And the same thing happens with these north poles. They're close to each other, so they push each other away. So this north pole is pushing the north pole on this bar in that direction. Okay? So this is acting to turn the motor around in this direction. So then if we wait just a moment later, this this bar will have turned a bit. So we still have our permanent magnet at the top and permanent magnet at the bottom. But now the bar has rotated around a bit. So now this south pole that was up here is moved down. So now you have the south pole from the electromagnet down there, and the north pole is now up here. Okay, you know, and this still has the wire wrapped all around it. All right, so now you've got a north pole close to a south pole. What do those two things do? Do they repel each other still?
Stick together.
Yeah, they attract each other. So now this north pole is being attracted to the south pole, which is good because that's still causing the bar to rotate in the same direction, which is what we want, right? We want our car to keep driving forward. Okay, so that's great, but we're coming up to a problem here. Anybody see what the problem might be?
How are they going to push each other away after the stick?
Right, exactly. When this bar gets perfectly straight up and down, now you're going to have a north pole right next to a south pole and a south pole next to a north. They're going to be attracted to each other. They're going to kind of want to stick there, right? So, but that's not what we want. We want this bar to keep rotating. So, anybody have an idea about what we could do to fix that and make this bar keep on spinning in the same direction? Yeah.
Pulse at a certain frequency, so like turn off the electricity at certain points to allow it to maintain.
Change direction of travel.
Yeah, exactly. So if we were to turn off the electricity right at that when the north pole got right to the south pole and vice versa, then it wouldn't stick. So that'd be good. And then, you know, just a fraction of a second after that, we'd be kind of in this situation here where the bar would have moved a little bit past that point. Now, it would be nice if we could get some magnetism to keep turning this bar around. But if we just put the electricity on the way we had it before, then we'd have the north pole up here again, and it'd be attracted to the south pole, and it would tend to pull our bar back in the opposite direction. So we don't want that. So is there any way we could make this bar keep spinning farther on?
Like change the direction of current?
That's exactly right. Yeah. Remember, we said that when we change the direction of the current, we change the location of the poles. So now, if we change the electricity direction, now we can create a south pole up here and a north pole down there, and we're back to where we started, where the south poles are repelling each other and pushing this bar around. Same thing with the north poles. And so then the whole motor keeps on turning, okay? So that's the basic way that an electric motor works. We have this electric magnet in the middle, permanent magnets around the sides, and we push electricity through the electromagnet until the poles get close to each other. And when the poles get close to each other, we reverse the flow of electricity so that they don't stick and the motor keeps on turning, okay? Now, yeah.
So same way you put those wires, you change them?
Yeah.
That's how it...
Well, that's a great question, right? Now, if I was shrunk down really, really small and I was sitting inside of that motor, I could kind of be in there and you know, connect one thing to someplace out, you know, and then disconnect it and connect it to the other place when it was time. But it'd be really hard for me to fit inside a motor, right? So, but that's a great question. We can't just have these two wires permanently connected. We have to be able to switch them around. And so the way that works is with some little devices called brushes, okay? So basically, if you look at the shaft of a motor, say we're looking at it from the side now. Or no, say we're still looking at it from the end on. It'd be like that. There are electrical connections around the outside of this shaft. So it might be something like that. That would be one connection, and then that would be the other connection. And there are these little attachments that bring power to the shaft. So like this would be the positive voltage, and then this would be a negative voltage. So what happens is that this positive voltage is touching this connection, and the negative voltage is touching this connection. And then as the shaft turns around, at some point, the little electrical connections on the shaft are going to rotate so that now the negative voltage is connected to this one up here, the positive voltage is connected down there, and that's how the polarity is changed. So it's all done mechanically, okay? And with a real, I've drawn this in sort of a simplified way to show you what's going on. In a real motor, it's very similar, but there's just more sets of these magnets. So there'd be one here, and then another one there, and another one there, and basically the bar would switch off polarities every time it went from one magnet to the next to the next. So this shaft has not just two electrical connections around it, but many. Okay? And I've actually brought along a motor where you can actually see this happening. Okay? So, and then, yeah, down here is the same thing. So these connections are called brushes because they used to be made with little tiny wire brushes. Okay? They were literally metal brushes with lots of little tines that would touch these metal connections. But they found that these tines had a tendency to break off and wear out over time. So now these connections are made usually with blocks of graphite. This graphite has very low resistance, and it's easy for it also has low friction, so it's easy for the block to turn, for the shaft to turn. So these blocks of graphite are pushed against the shaft, and they make connections with these little electrical terminals around the shaft. So I brought along this motor where you can actually look inside it and see this happening. So if you look in through the little ports, I'll pass this around in a second, but if you look in through the little slits in the side of this motor, you can see the shaft and you can see these little electrical connections there. And then in these narrower slots, those little those slots show these graphite brushes that are being pushed up against the shaft. You can see where those graphite brushes are actually touching the electrical connections in there. And then down below, you can see electrical windings, coils and coils of wire. And those are the electromagnets that are around the shaft of this motor. Okay, so this is a motor that came out of a weed whacker. So it's a pretty common thing. But you can really see what's going on inside there. Yeah?
Will you be interested in checking out a small transformer of sorts?
What do you mean?
It's a bunch, it's a really old transformer.
Yeah.
It's quite literally just copper plates just put together.
Sure. Yeah. Yeah. Bring it in. We'd love to take a look at it. Yeah. Okay. So that's the basics of how a motor works. Okay. So this is called a brushed DC motor. It's called brushed because it uses these brushes, and it's DC because we supply DC electricity to this motor. Okay. There are other types of motors, but I don't want to go into them right now. But this is a common type of motor called a brushed DC motor. So any questions about that? Okay, so that type of motor can make this axle turn. Okay, now if we supply a constant electrical voltage to this motor, it's just going to keep turning and turning and turning in the same direction, which is great for making a car drive forward. But if we're working with robots or windshield wipers, we might want to be able to have more precise control over the motor than just making it turn in the same direction all the time. So in order to do that, we can use something called a servo motor. And a servo motor is an electrical motor, just like we talked about, plus a little computer brain that is attached to it. So what happens is that this computer brain is listening for messages all the time. So we can send a message to this computer brain and tell it, hey, turn the motor at a really fast speed. And then this little computer brain will increase the voltage to our motor and make it turn fast. Or we can say, okay, make that motor turn slowly. And then the little computer brain will get that message and slow down the motor. Or we can even say, okay, make that motor turn the opposite direction now. And the little computer brain will receive that message and make the motor spin the opposite direction. Okay? So, yeah, and it's possible to make these motors spin the opposite direction too. All we would have to do is switch the polarity of the electricity that we're applying to these brushes, and then the motor would start turning the opposite way. But yeah, again, we'd have to be in there and controlling that. Whereas with the servo motor, it has this little computer brain that does all of that for us. Okay? So I've actually got a little servo motor that we can look at as well. So the servo motors that we're going to be using in this class look like this. They're very common. They're called hobby servo motors because they're used in remote control hobby cars and airplanes. So these hobby servos are very common. And I've got one that's taken apart so we can actually see what's inside. So this is one part of the hobby servo. So if we pull this apart even more, we can see that this is what we got inside. So this little silver metal can is the motor, and there's a little axle that's coming out of the motor, so that's what actually turns. And then all of this, these chips back here, one is the little chip that listens for the messages that come over, and then the other one is the chip that actually controls the electricity going to the motor. So it's kind of like an on-off switch or a speed control switch. And then the computer is what actually controls the speed. All right. So this is actually the inside of the hobby servo. So it's got the motor and the brain. Okay. But there's one more part to the servo as well. And that's the part that goes on the front of all of this. Here it is. So if we look at a hobby servo, it looks something like this. So we already talked about the back part, that's the motor and the brain, but then the front part has gears in it. So these gears are kind of like a transmission in a car. They take the motor motion that's coming out of here, which is actually really fast but doesn't have very much power or very much force. And they change that so that it goes slower, but it's got more force, so it can actually move the motor, or move your robot around on the floor. Okay, so that's really what's inside of this servo motor. So it's the motor, the brain, and a gearbox. Okay, so I'll pass this around so you can take a look at that as well. The gearbox has a piece of tape over it. Please leave that on there because it's holding the gears in place. We don't want them to fall all over. Okay. All right, so that's what a servo motor is. It's a regular electric motor plus a brain that receives messages. So if we want to use a servo motor, we need to understand how we send it messages so that we can tell it what to do. So when we have a computer and it's talking to something else, it uses a language, and we call that language a protocol. So let's talk a little bit about the protocol for communicating with these hobby servo motors. So the way that we send messages to these little hobby servo motors is that we send voltage pulses. So if we were to look at a message and we were to measure the voltage and see how it changes over time, we would see that the voltage starts off low, and then, so it starts off at 0 volts, and then it goes up to 5 volts for a short amount of time, and then it goes back down, and then we wait, and then we see another pulse up to 5 volts, and then we wait, and so on. So it's the amount of time that this pulse lasts that really contains the information. Okay? So we call this the pulse width, because if we're looking at it on a graph, it's how wide that pulse looks. But really, it's an amount of time that that pulse is high. So this pulse width tells the motor what we want it to do. So, a pulse width So if we have a pulse width of 1 millisecond, that tells the motor to go full speed clockwise. And then if we have a pulse width of 2 milliseconds, that tells the motor to go full speed counterclockwise. So what do you think it would mean if I sent the motor a command of 1.5 milliseconds? Any idea? Well, 1 millisecond is full speed in this direction. 2 milliseconds is full speed in that direction. Yeah? That's exactly right. 1.5 milliseconds is right in the middle, and halfway between full speed that way and full speed that way is stopped. So 1.5 milliseconds tells the motor to stop. And then we have kind of gray areas in between also. So say, 1.6 milliseconds is, it's between stopped and full speed clockwise, so it would be slow clockwise. And similarly, I went the wrong way. 1.4 milliseconds would be slow clockwise. 1.6 milliseconds would be slow counterclockwise. Okay? So we can, if we send these different pulses to the motor, different pulse widths, we can tell that motor what we want it to do. So the pulse width is really what determines the what message we're sending. But we also, there's one more thing, and that is the time between these messages. And that's always 20 milliseconds. So that never changes. That's always 20 milliseconds, okay? So that doesn't have any information. It's just always the same, always 20 milliseconds. Okay. Yeah?
20 milliseconds between the start of each pulse or the end of the last one and the start of the next one?
Yeah, so there's a little wiggle room. You could, the easiest thing to do is just between the end of the first one and the beginning of the next one. Yeah. Yeah. Right. So other questions about that? Okay. So then so now we know what we want to send. The next question is how we can actually do that using our basic stamp, because that's what we want to do. We want to use our basic stamp to control this servo motor. So, we've already seen that we can make a delay in our program. So we might think about that as kind of being the first thing to do. But that delay is just not very precise. We can make a delay of 1 millisecond or 2 milliseconds, but we can't really use that delay command to create anything in between those two. So we need a different command to create these pulses. Fortunately, there's a command that does exactly that, and it's called pulse out. So P-U-L-S-O-U-T. It should have an E in there for pulse, but it doesn't. It's just P-U-L-S-O-U-T. And the units are kind of weird on this. So pulse out 500 equals a pulse of 1 millisecond. So that would be full speed clockwise. Pulse out 1000 is 2 milliseconds. So that's full speed counterclockwise. And so right in between them is pulse out 750. And that's 1.5 milliseconds, and that's stopped. Okay, so, and then we can use other numbers between these values that can make the motor turn more slowly in one direction or the other. Okay? So that's how we can send messages to our servo motor using our basic stamp. So are there any questions about that? Let me get this cart out of the way so it's easier to see. So any questions about that? Yeah.
So if we apply the voltage 5 volts for 1 millisecond,
Yeah.
it turns full speed.
Right.
And if we increase the time to 1.4, so 5 volts will last for 1.4.
Right.
So why it slows down?
So we're not actually using this to send power to our motor. We're just using this to send a message to the little servo brain. So a pulse of 1 millisecond tells the servo brain, okay, make that motor spin full speed clockwise. If we increase this a little bit and make it 1.4 milliseconds, that's just sending a different message. It's sending a message now that's saying, okay, make that motor turn slow in the clockwise direction. So it's just sending different messages. Yeah?
Does the pulse width always have to be 1 millisecond equals full speed clockwise, or can you change it to your desire?
You can't change that. That's part of the protocol. So people got together in a room a long time ago and decided that that's what 1 millisecond is going to mean, and that's what 2 milliseconds is going to mean. And then you can go in and play around with what time you send, but you can't change the protocol. Yeah?
I have a quick question on the slowest, the first one, 1 millisecond,
Yeah.
full speed clockwise.
Yeah.
There's the counter, is that just, normal counter, 1 through 10? The 2 millisecond, full speed counting clockwise? Oh,
So-
never mind.
Yeah, it's just the opposite direction. Yeah.
counter.
Yeah, but that brings me to a good point. As soon as the motor stops receiving these pulses, it's going to stop turning. So if it waits for like 25 milliseconds and it doesn't get a new pulse, it's going to say, okay, I'm done with my job now. I'm just going to not apply any more power to my motor, and that motor is just going to stop spinning. Okay? So if you want this motor to keep turning, you have to keep sending it messages. So like turn, 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 turn. As soon as you stop telling it to turn, it's going to stop turning. Okay? So yeah, are there other questions about this? Okay, so then let's go on and do a preview of today's lab. And like I mentioned earlier, we're going to get to actually play with these motors and make them turn during our lab. Okay, so the first thing that we're going to do is this lab shows that we should create this little circuit here. Okay, so let's create that circuit. So this shows a 1 kilo ohm resistor going from P1 to VSS. So let's do that.
Okay.
So you don't have to do it at the same time that I'm doing it. I'm just going to do a demonstration, and then when it comes time for the lab, that's when I would recommend that you actually work on it. Okay, so it said a 1 kilo ohm resistor from P1 to VSS. Okay, so if we look over here, P1 is way down here and VSS is way up there. If we try to stretch a resistor from there to there, yeah, it's going to be a really tight fit. It probably won't stretch. All right. Fortunately, there is another P1 that we can use. So if we look right here, there's this other spot that is labeled P1. So we can use that. So if I take one end of the resistor and stick that there in P1, that's a little bit closer. And then the other end of the resistor can go over to VSS. Oh, and we got that echo going on. It's this microphone in the webcam here. Sorry about that. All right. Okay, so, all right, so now we've got, and I made a mistake here. I connected this resistor over to P3 when I meant to connect it to P1. So it's really easy to slip up, so you've got to be careful where you're putting that. Okay, so the resistor is going from P1 to VSS, so that's what we want. And then the other thing is we need a wire that can go from P1 to VDD. Okay, so there are little jumper wires, just little pieces of straight wire that are available. So we can take one of those and connect it from P1 to VDD. All right, and that's the first part of the circuit. Now the other thing that's shown here is we want a resistor going from 407 from P2 to an LED and then to VSS. Okay, this one is 470 ohms. The first one is 1 kilo ohm, so that's a brown, black, and red marking, and then the 470 is yellow, violet, brown.
470 is yellow, violet.
Yeah, yellow, violet, brown for 470. So, so I got one of those right here. So this one is going to go start in P2 and then connect to an LED. So I'm going to take the end of this wire and put it into P2, and then that'll come over here somewhere in the board. And then we'll get an LED. And that'll go from this resistor down to VSS. And again, remember that LEDs are polarized, so you need to have the flat side pointed, the flat side of the case going towards VSS. All right, so that should be our circuit there. And then it says you want the wiper stroke to be approximately 180 degrees. 180 degrees counterclockwise and then 180 degrees clockwise back to the original starting point. And then, so we should hook it up the way that it's shown here and then run our basic stamp program. So the basic stamp program for today is located in instructor files and then ET302. And then this is LO2, stamp 2. And then windshield wiper new is the one that we're going to start with. The last thing that we want to do is that we want to connect our motor to our board. Okay, so in the program we're going to be sending messages on pin 12, but this is the little end of the motor cable. It's not going to be easy to plug this little connector into the little hole that says P12 on the board. Okay. It just wouldn't work very well. Fortunately, the people who make this basic stamp know that people often want to control motors using the stamp, so they have helpfully added these extra ports up here at the top where we can connect these servo motors. So these ports are labeled 12, 13, 14, and 15. And so what that means is that when we send a message on pin 12, it goes to the little port 12 on the board, but it also comes up here. And if we plug this servo motor into this port at the top of the board, the servo motor gets whatever messages we're sending on pin 12. So we're going to attach that up there, and there's an orientation that it has to go in. So you notice that the cable has a red wire in the middle, a white wire, and a black wire on it. And this board is also labeled with red in the middle and black on the bottom. So when you plug this cable in, you need to make sure that the black wire goes towards the bottom of the board, otherwise it just won't work. Okay? So I'm going to take this cable and plug it in to this port on the right that's labeled pin 12. Okay? And I'm going to make sure that the black cable is towards the bottom of the board so that it gets messages on the correct side. All right, so that's how we connect our motor. So now that we got our motor connected, let's send over our program. So we'll come to this program and we'll send it over and just see what it does first, and then we can go back and try to understand why it works. So we'll send this over, and when I send this over, right now nothing's happening. The motor isn't turning, nothing's going anywhere. And there's a reason for that, and that is that right now I have this switch at the bottom set in position 1. So there's actually 3 positions for this switch. Position 0 means off. Position 1 turns on everything on the board except for the motors. And then position 2 turns on everything including the motors. Okay? Now the reason for this is because starting next class, we'll actually be making a little robot that drives around. And you can imagine if you have a program that's written to make your robot drive forward, and you've got everything turned on, and you send over that program, the first thing that robot's going to do is drive right off the edge of your table. Okay? So it's nice to be able to turn on everything except the motors so that you can send over that program and get it all into your robot and ready to go without having your robot drive away. Okay, so that's why there's these 3 different positions. So right now I have this in position 1, which is turned on everything except the motor. So now hopefully when I move this over to position 2, the motor will go on. Let's see. There it goes. All right, so that's what our program is doing right now. It's making the motor turn back and forth, and that's what we want. So this is great, but it's not ideal because really that motor is turning way too far. So yeah, if we had this on a car, that would be wiping our windshield and then wiping our hood, and windshield and hood, and then go back the other way. Windshield, hood. Yeah, so it just wouldn't work out very well. So we want to be able to turn this program and change it a little bit so that the motor only goes back and forth like this, kind of a half circle, okay? So let's look at our program to see how it's working and maybe how we could fix this. Okay. So the first thing that we have in our program, well, let's look at this part first. This part says windshield clockwise. Okay, so this is making the windshield wiper turn clockwise. So this is for counter F1 equals 1 to 100. We're going to do pulse out on pin 12 for 500. So remember, a pulse out of 500, what does that do? What does that make our motor do? Right? Oh yeah, that'd be good. Yeah. Now, so what does a message of pulse out 500 say to the motor?
That's how far it's going to push.
Almost, not how far, but
1 millisecond.
yeah, how fast?
Full speed.
Yeah, so exactly, it's full speed clockwise. So we're creating a pulse that's full speed clockwise, and then we're waiting for 20 milliseconds. Remember, that's the time between those pulses. And now if we sent it just one pulse, what would the motor do after after that single pulse? Would it keep going?
No.
No. Right. As soon as we stop sending pulses, the motor would stop turning. So if we want it to keep going, we have to send it more than one pulse. So you'll notice that this pulse out and this pause are actually inside of a loop. So this loop here, this is a for loop, and it runs from 1 to 100. So how many pulses are we going to send? 100, exactly. We're sending 100 pulses up here because the loop runs from 1 to 100. So, so that's what's going on there. And then, so if the motor is turning too far clockwise, what could we make it do to turn not quite so far clockwise?
Change the speed.
Yep, so there's kind of two things we could do. We could change the speed and make it turn more slowly, or we could change the number of pulses to make it turn for not quite as long. So, so let's look at the pulses first. So instead of making this 100, let's make that 50. So we'll send this over, and then let's look at our robot here. All right, so now we'll turn this on. So it's still going pretty far counterclockwise, but it's going not quite as far clockwise. So yeah, so we could make this 25 instead of 50, say. And we could do the same thing for the counterclockwise. And we could send that over. And now when we run it, so that's pretty close, okay? So so that's one way of controlling the distance that this thing turns. All right, so let's look at the lab and see what it's asking us to do. So it says the first thing we should do is adjust the wiper stroke to be about 180 degrees, about half a circle. So we did that, and then we use this program. And then after you make it go back and forth at high speed, like that, it says you can modify the program and make it go very slowly. So you would want to change the speed and make the speed very slow, and then also make it go back and forth half circle. Okay. So when it's very slow, still going back and forth half circle. This would be like if the rain is just kind of misting down, and you just want those wipers to go back and forth very slowly. You want to program your robot to do that. And then finally, the last challenge is to add a speed controller. So this would be like the little switch that you use on your car to switch between fast and slow. Okay? So the way that we do that is that we actually have to sense a voltage. So so that's what we're doing up here in this program. We're using this this if statement. So we're looking at pin 1, and we're saying that if in1 equals 1, that means that if we're getting a high voltage on pin 1, then we do all of this stuff. Otherwise, we do nothing down here. So right now, we're looking at the voltage on pin 1, and if it's high, then we do this. We make the windshield wiper go back and forth. Otherwise, if it's low, we make it do nothing. So you might wonder how we're getting that high voltage on pin 1. Well, the way that we're doing that is with this wire. So that's what the wire is for. So when it's in this position, we're getting a high voltage. It's bringing the high voltage from VDD down to pin 1. When we move this wire away, it's no longer supplying that high voltage and the motor stops moving. So we can move this back and make that motor start spinning again. Now, for the second part of this program though, or for the second part of the lab, we want to be able to use that to control the speed of the motor. So there's actually another program for that, Windshield Wiper Part 2, it's called. So we can open that up. So here, it's saying that if the voltage is low, then you'll do this stuff, which makes the motor spin quickly. Otherwise, this else says, do this stuff down here that makes the motor turn slowly. Okay? So, so when we run this, and we run our program, this should make the motor turn quickly when the wire is in that position. But now if we move this wire, it should make this motor go back and forth slowly. Okay? So you can see that wire is now acting like a speed control. Okay? But you can see this program still isn't perfect. You still need to make some modification because that's not going back and forth a half circle. It's only going back and forth a tiny bit. Okay? Yeah.
So right now it looks like, right now we have 2 different timings on, and it's doing like a circle, run back, and going farther than it was before. Starting the bottom, just doing that.
Right.
If we do speed with the same numbers, it'll do that a lot quicker, but not give you the half rotation. What I'm saying is, with the timing you can get the right rotation on low speed, but changing it to high speed, it feels like you wouldn't get the same time. It seems like it.
You're right. So when it's going on high speed, you only need to make it move for a short time to get from one side to the other. Whereas when it's going on low speed, it takes a lot longer for it to get to from one side to the other. So you need to adjust the amount of time that it runs in those different cases. It's not going to run the same amount of time back and forth on high speed as it does on low speed. Is that what you're asking?
Yeah.
Yeah. Yeah. So you need to play around with that and figure out those values that work for both.
Let's do it.
All right. Yeah. Other questions? All right, then I'll take attendance and yeah, we can get going.